Here in section 2.3, we meet our first calculus theorem. So before we talk about the intermediate value theorem, I want to call to your attention the fact that reasoning with theorems and definitions is one of the big things you're going to be expected to do on the AP test. Now, I think you already know how to do that, but we haven't done it with calculus yet. So we're going to take a quick detour, remind you what you already know about reasoning with theorems from geometry, so that when we meet the intermediate value theorem, we'll be able to apply it. So I found this online. This is just a little screenshot. This is the vertical angles theorem, which perhaps you remember from geometry. And a quick reminder, a theorem is a statement of fact, a truth that can be proven. So somebody somewhere proved the vertical angles theorem, and then your geometry teacher probably made you prove it again. But then after enough people have proven it, and enough people have seen the proof, and they're like, oh yeah, obviously vertical angles, they're equal. We stop proving it every time, and we all just agree. Well, we all believe the vertical angles theorem, so we're just going to accept it as true. So you might see this. It says if two angles are vertical angles, then they have equal measures. And then once you were convinced that that's true, either by proving it yourself or because you read it in a book and that was convincing enough to you, then the next day when somebody asks you, what is the measure of angle LHM, you don't feel like you have to go through the process of proving the vertical angles theorem. You would probably just say something like, since angle KHO and angle LHM are vertical angles, then the measure of angle KHO equals the measure of angle LHM, and therefore the measure of angle LHM equals 129. Notice here two important parts of the theorem. We have this word if and then. So if two angles are vertical angles, which means don't bother trying to convince me that two angles always have equal measure. This only applies if the two angles are vertical angles. So it's the part that has to be true, and then if you promise me that part is true, then the rest of this will be true. So look at what happens in our, since that thing that had to be true is true, the angles are vertical angles, then it must be true that they have equal measure. So we're going to use that same process, this idea of starting with an if-then statement, and then being able to say, okay, if the if is true, then the then must also be true. So this will bring us to our first theorem in calculus. It's called the Intermediate Value Theorem. Remember, our context, what we've been learning about in this section, is continuity. So what does it mean for a function to be continuous? Informally, it means you can draw it without having to pick up your pencils. There's no holes, there's no skips, there's no jumps. And that's, the intermediate value theorem is sort of an application of continuity. So there's a version here in this yellow box, there's a version on your paper. I'm going to highly recommend that you pick one of them and memorize it. So the intermediate value theorem, if a function is continuous between a and b, then it takes on every value between f of a and f of b. So suppose k is any number in between f of a and f of b, then for at least one c, and c must be between a and b, f of c equals k. So take a second, there's a place on your paper for you to stop and figure it out. So in the intermediate value theorem, is k an x value or a y value? Meaning, is k an input value or an output value? And I want to ask the same question about c. Is c an input value or an output value? So take a second, look at the notation here, see if you can answer that question on your page 3, and then restart the video. All right, I hope you concluded that c is an input value, and k, in this context of the intermediate value theorem, is an output value. So I'm sure you promised me that you're going to remember the intermediate value theorem, but we have to know, what does it mean for us? They're very good on the AP Calculus program about not just memorizing stuff to memorize it. What is it going to mean to us? So notice here I've added two little dotted lines to this picture. If k is some y value, In our case, it's going to be a y value that we're interested in for some reason. If I have 2 points on my graph, let's get the marker here. If I know 2 ordered pairs, let's call that A, comma, f of A, and B, comma, f of B, and there's some y value in between the 2 y values I know that I'm interested in, then somewhere in between the 2 x's I have, there must be an x. In this notation, it happens, we call it C, just to give it a name. There's a C value, and at that place, there's at least one place where it happens, and the output value, the y value there, is k. So really what this means is, since we're promising that the function we're talking about is continuous, and I know one y value that's smaller than the y value I care about, and one y value that's bigger, since the function is continuous, I know that the function can't skip over my y value. If it got from here to here, it must have crossed over that y value that I'm interested in. Otherwise, that implies that it must have somehow skipped over, but we've been promised that our function is continuous. So that's what we're going to use the intermediate value theorem for, to prove that when there's a y value we're interested in, that there must be some place on the graph where that y value gets touched. I promise we're going to do lots of examples. So here's just one more picture. This is from your handout. Another way, just another example of how to think about the intermediate value theorem. So here's some function, call it f of x. I can see that it's continuous. There are no holes or skips in it. And pretend there are these 2 points, these red dots here that I've drawn in, and I know those ordered pairs. If there's some k value, some y value that I'm interested, that's between the 2 y values I know, then that dotted line at y equals k, I am guaranteed that it must touch my function at least once. So my question to you, this is just a made-up picture, how many times does the function y equals k touch my function f of x? So here it just happens that there are 1, 2, 3 places where that happens. The intermediate value theorem guarantees that there must be at least one. It doesn't say anything about it happening more than once or whether it can or can't happen more than once. And it doesn't even tell us anything about how to find where it does. All it does is guarantee that there's at least one place where f of c equals k. And that c has to happen at least once in between the a and b, in between the 2 x values I know. So try this first example. So here's an example we're going to answer using the intermediate value theorem. Assume that f of x is a continuous function. I don't know anything about f of x except I know f of -1 is 2 and I know f of 5 is 4. That tells me that I have ordered pairs -1, comma 2 and 5, comma 4. And that somehow those 2 ordered pairs are connected with no skips or jumps or holes. So this is the information I've been given, and I've been asked to explain why there must be a value c for which f of c equals 3. So my recommendation, especially as you're getting started with the intermediate value theorem, is that you try to make a graph to help you. So in order for the intermediate value theorem to work, you have to know at least 2 y values on your function. And it has to be the case that the y value you're interested in, notice 3 is a y value, has to come in between the 2 y values that you know. So check this out. I know -1, comma 2. Pretty good. I know 5, comma 4. I know these are both on my graph. I don't know anything necessarily about how those are connected, except that they're connected in a way that's continuous. No holes, no skips, no jumps. What's the y value I'm interested in? The y value I'm interested in is y equals 3, because I've been asked to find prove that there's an x value, c, that makes the y value 3. So especially if you draw in this green dotted line, now you can see there's no way to connect the two blue dots without crossing over that dotted green line. So that's why making that picture can really help you. So we had the intermediate value theorem. If f is continuous on the interval a to b, then it takes on every value, every y value between f of a and f of b. Well, in this case, my a and my b are my a and my b are -1 and 5. My f of a is 2. My f of b is 4. So the question is, do I have two y values, one bigger than and one smaller than my target y value? If I do, then I'm going to be able to apply the intermediate value theorem. So here's your first step as you write up your answer. You want to show that you've recognized that you have a y value on your function that is bigger than the y value you're interested in, and you have one y value that is less than the y value you're interested in. So here's what I've written. I knew that f of -1 was 2. And that's smaller than my target y value. So I've written f of -1 is 2, which is less than 3. And I've written f of 5 is 4, which is greater than 3. So I have two y values. One is bigger than 3, one is less than 3. And the intermediate value, the continuity of the function tells me that my function has to take on every value between 2 and 4. And one is bigger than 3 and one is smaller than 3. So somewhere I'm going to have to cross 3. So start by making this statement. I like to make it in symbols. You could have written this out in words. And then now we're going to make our conclusion using the intermediate value theorem. I'll show you how to write it. For the intermediate value theorem to apply, we have to follow the first part of it. The if part of the intermediate value theorem is if f is continuous. So I have to show that I've at least thought about making sure I meet that requirement. So that's why I start here by saying, since f is continuous on the interval, and intervals are x values that I care about, then now the intermediate value theorem guarantees me that there is at least one number c. C is an x value, so it comes in between, the x values I know, such that f of c, the output, is 3. All right, so make sure you have that justification written in on your notes paper. Some calculus students look at the next page and panic. So I want to make sure that that's not the experience you have. If you're ready to take a look at the next page, that's fine. What I want you to do is to remember to focus on, is there a target output value that you're interested in proving the existence of? And can you find two ordered pairs on your function, one which is higher than and one which is lower than that target output value? And I'm going to suggest that you make a picture and then compare your picture to what we did here. If you're not ready to look at the next page, just make sure you have this justification, these notes written into your paper. Come to class Monday and we'll do them all together.